Okay, so this video shows the various functions for Olivine-Liquid Thermometry available in Thermobar, as well as various equilibrium tests. So as normal, go into the examples folder, the liquid Olivine-Liquid folder here, and then we're going to click on this Olivine-Liquid Thermometry Python notebook. And again, you can go into the examples folder on your sort of navigation on your computer, and we can look at the spreadsheet it's reading in as well. So first I'm just going to clear my kernel just so it looks like it does on your computer. Okay, so if you haven't installed Thermobar, you need to do so here by uncommenting this. Then load in various Python things. And we can see that this example is reading from the spreadsheet liquid only thermometry to start with, and the sheet name liquids. So we can have a look at that. So liquid only thermometry. So you can see here that this does in fact have liquid compositions with your normal underscore liquid. It also has a column for entering the proportion of Fe3+, which is fixed here at 0.2. And then there are also olivine compositions paired to these liquids along here. Okay, so first we read this in, we call the dictionary out, and then from this out dictionary we extract all the input columns as my input, the liquids as my liquids 1, the olivines as my olivines, and then we can just display these and have a look at the first 5 rows just to check that they've read in correctly. So you can see the only columns which are zeros for olivine is sodium and potassium, which we didn't enter, and nickel. And then for liquids, again, none of these columns we expected to have anything in because we didn't put them in our spreadsheet. So it has been shown many times that olivines and liquids are often out of iron-magnesium equilibrium. So by default, when you use the function calculate olivine liquid temperature, it's going to return both a temperature and a measured KD value between your olivine liquid pair. So for this function, we have to tell it the composition of our liquids, which is this data frame my liquids that we made above, your olivine compositions, which is this data frame my olivines that we made above. You then need an equation for temperature. So here we're using equation 22 of Peterka 2008. We need a pressure. So here you could either use a fixed pressure, and the examples for this are shown in the liquid only video, which is probably worth watching. But here we've chosen to use a different pressure for each calculation. So we're using the pressures stored in the column P kilobar in my input. So you can see here, these are the pressures that it's using. So a different one for each row. And finally, we're going to use a proportion of iron 3+ of 15%. And this is because the way that Thermobar works, only iron 2+ is used in the liquid when assessing partitioning between the olivine and the melt. So we can run this. And we can see here are the temperatures that it's calculated on the left, and here are the KD values using the iron and magnesium in the olivine and the liquid, and only the 2+ for the iron. So we can see that, you know, maybe this one is in equilibrium, but these values are pretty low and these values are pretty high. So what you might want to do, and you should probably always do when you're doing olivine liquid thermometry, is you can add this extra line, EC tests equals true. And this means it will not only calculate the temperature and the measured KD, it will also calculate a variety of preferred KD values based on various models. So again, we have the temperature here, we have the KD that we've measured, and then we have the KD calculated using topless. We have the delta KD value, so that's the calculated and measured, the difference between those for topless. We have the KD for Roeder and Emsley, so that's using the ideal 0.3 value, and the same for Matson. And then it also returns all of your inputted things, so your liquids, your olivines, and also all of the cation fractions and various things used for the calculation that you might want to plot against your temperatures, for example. If you get one of these data frames and you just want to access the temperatures, as always, you take the name of the data frame, use square brackets, and then the name of the column in quotes, and here we can minus 273.15 to get temperature in Celsius. So we can see here are our extracted temperatures. Say we only care about temperatures where the value of this delta KD, using the Roeder and Emsley model, is less than 0.03. We can do this using the lock function. So what we do is we say, I want the temperatures in equilibrium. So basically I'm going to take my data frame and I want all the values of that data frame where delta KD Roeder is less than or equal to 0.03. And we can run that, and you can see you get all of the columns, but only a single row, so only one of these is in equilibrium. If you just wanted the temperatures, instead of returning the whole data frame, you could just put the temperature calculated here, and then it would just give you a single temperature. So this is a common problem in that you don't have any equilibrium olivines, or you only one. So what you might want to do is maybe change the proportion of iron 3+. Maybe this is why you haven't got any matches. So what you can do is, by default, it is always reading the proportion of Fe3 plus Fe total that you gave it in your spreadsheet. But you can change it here, so you can overwrite it in the function, and here we can increase it to, say, 0.3. And you can see now maybe this one is in equilibrium, but you still haven't got a huge number more matches. So what you might want to do is you might say, okay, I've got these liquids, what olivine compositions would I expect to be in equilibrium with them? So you can start comparing those to your measured olivines. So we have this function, calculate equilibrium olivine content. And what this does is it takes, you give it your liquid compositions, you give it a KD model, so in this case we want to calculate the equilibrium olivine compositions using Roeder and Emsley, and we want to perform those calculations using 20% iron 3+. So we can run this, and you can see what it does is it calculates the magnesium number for your glass using only iron 2+. It calculates the magnesium number using iron total, and it calculates the equilibrium forsterite content. Here for KD is 0.3, so that canonical value, and that is using the magnesium number Fe2. So if you wanted them to be the same, you would just simply put 0 here instead of 0.2. And then it calculates sort of a value for this upper KD of 0.33 and sort of for the lower, so 0.27. So what you can see is that for your measured liquid composition, you would expect olivines between, say, 0.86 and 0.88 for this liquid. For this liquid, between 0.83 and 0.85. You can also put your olivine compositions into this function, again, if you want to. This is just an extra input. And what it will do then is it'll give you all of the same columns as before, the only difference being it has now added a column on the end which says forsterite measured, so you can compare these more easily. So you can say, for example, well, the ideal value for this is 0.84, but the forsterite I've measured is 0.9, so this olivine is too primitive for the liquid it's in. You can do the same thing as above, just say your liquids, but instead of using the KD model of Roeder and Emsley, you can do it for Matson. And then it tells you it has calculated this olivine using KD as 0.34 and the upper and lower values of 0.352 and 0.328. And again, you could add your olivine compositions in here as well if you wanted that extra column. Now the topless model is a little bit more complicated. While the Roeder and the Matson model are fixed values for KD, so that 0.3 and that 0.34, topless express it as a function of melt composition, pressure, temperature, water content, and the olivine forsterite content. So what you can do here is, again, you need your liquid compositions. We're going to specify that we want the KD model of topless 2005, specify an iron 3+ amount, and then we could tell it the pressure from our inputted data frame of pressures. So that was the input pressures in our spreadsheet that it's reading in. So these here. And say you have a temperature that you think you know. Now this is where it starts to get a bit backwards, but just bear with me. So for example, it could be taking the temperature from here. And because that's the temperature in Celsius, we need to add 273.15 to it to get the temperature in Kelvin, because every input in thermobar is in Kelvin. Finally, you need an olivine 4-stroke content. So you could say, okay, well, let's calculate this for a 4-stroke content of 0.8. And it will give you, again, your magnesium numbers of the liquids. It will give you the KD that it's calculated based on these parameters and the equilibrium 4-stroke content. You could do the same thing, but instead of specifying olivine 4-stroke here as a fixed value, you could feed it in your olivine compositions here, and then it will use the measured 4-stroke content to calculate the KDs. So you can see here that they're a little bit different. So now the equilibrium 4-stroke content is 0.89 rather than 0.86. However, this is all a bit backwards because you want to know your temperature. How are you supposed to, you know, do this if you don't know your temperature? How are you supposed to assess what's in equilibrium? And also, you're supposed to be knowing a 4-stroke content, but you're trying to calculate a 4-stroke content. So there are sort of 2 steps to how we can actually perform iterative calculations here. So if we use the function again, calculate equilibrium olivine content, we give it your liquids, you tell it your KD model is topless, you give it your Fe3, Fe total, you give it a pressure and you give it a temperature, but you don't give it an olivine 4-stroke content. What it will do is it will iterate the calculated KD and the equilibrium 4-stroke content until it sort of converges with your liquid. And it starts at a 4-stroke content of 0.95. So if we run this, you can see here are your magnesium numbers, but what it has done is it has now iterated KD and equilibrium 4-stroke content until it converges. So here your equilibrium 4-stroke content for these liquids is 0.86, and the KD that corresponds to these pressures, temperatures, and olivine 4-stroke content is 0.34 in this case. But, you know, this still requires you to know your temperature, which kind of defeats the point of doing Olivine-Liquid Thermometry. So what you could do is, if you really wanted to use the topless model to calculate equilibrium olivine content, you can take a first guess of the temperature. Now, Keith Paterka releases some Olivine-Liquid thermometers where instead of using the measured value of partitioning between magnesium in the olivine and the liquid, he substitutes that term using the theoretical value calculated from an expression from Beatty. So this is referred to as T. Paterka 2008 equation 22, which is the Olivine-Liquid thermometer, and then you've added BT-DMG on the end to show that you want the theoretical one, and this means you only need the composition of the liquids. So now what we can do is we can use the same function, but instead of guessing a random temperature or using it from our input spreadsheet, we can now put, we called this temperature, we calculated T-calc22, and we can put it in here. And now we can see using the BT model, all we've had to tell it that to get our temperature, we now can use topless, and all we needed was our liquid compositions, an estimate of the proportion of iron 3+, and a pressure. And we can say for this liquid, the equilibrium olivine content is 0.86. There are some other options. So Keith Paterka releases 2 equations, equation 8 and equation 9. And you can see again, these allow you to calculate the olivine 4-stroke content. And finally, equation 8b and 9b requires you to put a log FO2 in. So again, there you go, and you can get more equilibrium olivine content. So I think this is all the popular models you could want to calculate the equilibrium olivine 4-stroke content for a specific liquid. And if you want them all, you can simply specify KD model equals all. And it will give you all of them here. And you can see they're actually pretty similar, like Rhoda is about 0.87, Matson 0.85, Topless 0.86. They're kind of within reasonable scatter of one another. So a common way to assess olivine liquid equilibrium is to plot a Rhodes diagram. So we have built this function, PT calculate all Rhodes diagram lines. And what this does is you feed in your minimum magnesium number of your liquid that you want and your maximum magnesium number of your liquid. So here we want to perform calculations between 0.5 and 0.7. And what it does is it gives you an x-axis. This is just showing the first 5 rows. So the x-axis goes between your minimum and your maximum mg number. And then it gives you various lines that you might want to plot. So you've got the equilibrium olivine force-stroke content using that 0.3 value of Rhoda, using the 0.27, the 0.33 value, using Matson, and all along. You don't have Topless because of just how these diagrams work. It wouldn't be the same for each liquid because Topless is a function of your melt composition. So you can't do the standard plotting liquid and plotting olivine on because each liquid would have different lines. So now we can make a plot. The final things that we need to calculate is we need to calculate our olivine force-stroke contents. So there's just a simple little function here, PT calculate olivine force-stroke, and you just tell it your olivine compositions. And then we need to calculate a magnesium number for our liquid based on our inputs. So again, calculate Liq magnesium number. You just give it my liquids and your proportion of iron 3+ that you want. And then we can start to plot the results. So we make a subplot with 2 axes, AX1 and AX2. And then we called these outputs Rhodes. So you can plot on the x-axis the magnesium number of the liquid. And then we might want to plot 3 lines. So the first dotted line is going to be the equilibrium olivine. Value for KD is 0.27. 0.33 is another dotted line, and then sort of the mean value as 0.3 here. We can also plot on the second axis what the lines look like using the Matson model instead. So these are the various KDs. And this is what it looks like. So because we have plotted, the final thing we've plotted is this liquid magnesium number calc. So this is our liquid range of magnesium numbers and our olivine force-stroke contents for those pairs. Another thing you could do is you could use this nice Python function called fill between. And basically what this does, instead of drawing those lines as dotted, you can draw them as a nice filled region that you want. So in this example, this is using the full gap between the lowest value of Rhoda and the highest value of Matson, which is often used as a way to show this data. Now, you might say, for all of this, we're calculating the magnesium number of the liquid using a set proportion of iron 3+. But what if you don't know the amount of iron 3+? Well, what we can do is, again, we can maybe do a preliminary guess of the temperature. So here we're using an Olivine-Liquid thermometer, but equally we could use that liquid-only thermometer. And then we have this function, convert FO2 to Fe partition. So this uses the model of Kress and Carmichael. So what you have to give it is your liquid compositions. You give it your temperature. So here we're using a fixed temperature. So 1190 plus 273.15, but we could also use this temperature we calculated. We need a pressure in kilobars and an FO2. So here we're saying we want to evaluate this for NNO. And there's an offset. So because we've given it an offset of 1, we're actually evaluating it at NNO plus 1. And we're using the model of Kress 1991. And this will give you a variety of outputs. So we can just see what they look like to start with. So it'll kind of redo the oxide data and split it into FeO and Fe2O3 and give you this XFe3, XFe2 parameter. But what you actually want from this is this Fe3, Fe total liquid, and that's this column. So you can just dot it here, and then that will mean it returns that value. So now you can redo this calculate olivine liquid temperature again, but this time you can give as the proportion of Fe3 plus Fe total this value that you've just calculated here. And that will mean, because your equilibrium tests are true, that it's calculating the temperature, and then it is calculating all of these various equilibrium tests you might want to use using this calculated proportion of Fe3 plus Fe total.